Welcome back, everybody. We will start the next presentation. So Professor Marques-Silva will present us explainable AI on this presentation. So thank you, Marques-Silva. You can start.
Thank you very much. I hope you can hear me well, and my apologies for not being there in person. The title of my talk will be about applying SAT solvers in explainable AI, with trying to ensure the rigorous computation of explanations. I will explain what this means. So everybody's familiar with the many successes of machine learning. These days, everybody talks about LLMs. This is an old example of using an LLM to understand what a Sudoku puzzle was. It works very well in this case. Another example, and this is now really a hot topic, is to use LLMs for programming. So in this case, I use the LLM to help me with pandas. And of course, there are lots of other successes of machine learning. So there are lots of LLMs that are very, very well known. There are huge advances in image and speech recognition and so on. So there are no questions about the importance of AI in the present day. But there are some issues with the use of machine learning. So this is an example I created a few years ago. So asking the LLM how many pairs of twins you need in a room to have at least a 50% chance that two people have the same birthday. And of course, the solution for a human is usually obvious. And here in 2024, the LLM was giving a very, very incorrect answer. So it was giving the standard answer for this problem. 2 years later, a few months back, the situation remains the same. So it tries to fool the user with some explanation that does not make sense at all. Even if you accept this type of argument, this is a much more serious example that I came across a few months ago. So the question was, I need to get my car washed. I have to take it to the automatic car wash, which is 50 meters away from my house, just a few steps away. Do you think it's worth driving? Of course, for a human, it makes complete sense, the question, and of course, we know the answer. And here, the LLM completely crashes and says that, of course, you should walk to get your car washed, which doesn't make any sense. So there are, of course, lots of problems still with LLMs and with the ability to trust these systems. So what is explainable AI? So what happens is that these models are very complex and people don't really understand what is going on. And so the XAI is about helping humans to understand how machine learning models make their decisions. And people have focused on two types of questions when talking about XAI. Why the prediction? This is one type of question. The other type of question is, why not some other prediction? So my bank loan was rejected. What should I do to get it approved? And of course, an underlying question is rigor. So can we trust the methods that are being used for explainable AI? And here I distinguish between self-symbolic or non-symbolic methods and symbolic or logic-based methods. The importance of XAI is huge in Europe, but also in the US and of course in Canada, all over the place. So there are lots of regulations and recommendations for the use of explainability when using systems of AI. And in the case of Europe, there is a very well-defined characterization of when you can and you cannot, and when you should explain systems of AI. So there are situations where you should not use systems of AI. There are situations where it doesn't really matter. And there are situations deemed high risk where the use of AI should be very well characterized. So this includes high-risk applications, for example, law enforcement and management and operation of critical infrastructure, and among others, but also safety-critical applications, for example, self-driving cars, autonomous vehicles, and so on. Okay, and so this is so important that some researchers have proposed not using very complex machine learning models and instead using interpretable machine learning models, like, for example, decision trees. In any situation, the correctness of explanations is fundamental. So in these cases, we need the rigor of explanations to ensure that we trust what is going on, to diagnose systems of AI, and so on. And this is what we have been doing for the last 7 years. So the talk will give a brief overview, focusing on applications of SAT, of course. So the outline is well, we have to be on the same basis. So I will define the preliminaries and then introduce symbolic XAI, and then I will show you some results of when we use SAT solvers. I will focus on a very simple model, but I will also give you pointers to other applications. So to explain what is going on, we are going to consider a well-known class of machine learning models, classification problems. So we start with a set of features, and each feature takes values from some domain. So we can have categorical domains, discrete or real values, so we are not picky. Anything can be used. And feature space is the Cartesian product of the domains. And then we have a set of classes. And then essentially the machine learning model computes a classification function mapping feature space to classes. That's it. And what we want to do is, given an instance, which is a point in feature space and some class, we want to compute explanations for this instance. So even though I'm going to talk about classification problems, this framework can be easily extended to regression problems. So any type of machine learning model we can handle. So non-symbolic methods have been around for more than a decade, and they can be organized in 3 main classes. You can do feature attribution, where you assign importance to features, and well-known examples are Lime and SHAP, but also Selenium maps. And you can do feature selection, where the idea is that you construct a rule that explains the prediction that you are making. And a very well-known example, non-symbolic, is anchors. Finally, there is what people call intrinsic interpretability, where the explanation is given by the model. So you can, in this case, you can use decision trees or decision lists and so on. And these are essentially the main approaches that exist for using non-symbolic methods. So some examples of how these tools are used. So if you use anchors, it produces rules, and the rule is something like this. So if you have a bunch of conditions, then you can predict that some class, in this case, salary, will be greater than 50K. So this is what anchors is going to compute for you. For feature attribution, a very, very well-known example is SHAP, where instead of constructing rules, it assigns importance or relative importance to the features. So I will focus on local explanations. So in this case, given some instance, you can look at this graph and you understand that age and then some other features are more important, much more important than other features. And so what I should say about these methods is that they are model agnostic. So they ignore the machine learning model. They sample the model, that's it, and they offer no guarantees of rigor. So before I proceed, I don't have time in this talk, but I've given talks where this is covered and we have papers on this. So we have proved that all these methods can give you incorrect results. So you should not trust them in general. So there are a bunch of publications on this. And so this is the motivation for using logic-based methods for explainability. So let me introduce what we understand by symbolic XAI. So I'm going to use very simple examples so that the concept can be conveyed. This is an example of a decision tree. So you have features 1, 2, 3, and 4, and all of them are Boolean. And so feature space is 0, 1 to the 4th, of course. And you have 2 classes, 0, 1. And so essentially, for example, if x1 is 1 and x3 is 0, then you predict 0, and so on and so on. And I believe you saw this already in the summer school. And so an objective explanation answers a question, why the prediction? And it answers this question with a rule. So if some condition holds, then the prediction is what we are interested in. So concretely, if you have not x1, not x2, and x4, not x1, not x2, and x4, so we all agree that the prediction should be 1. Okay, this is an example of a rule we would like to generate. A contrastive explanation is different. So it answers a why not some other prediction question. So for example, if for this same instance, 0, 0, 1, 1, so I'm here. If I keep x1, x2, and x3, and I just change x4, so if I go from here to here, then I can change the prediction from 1 to 0. And so this essentially tells me how can I, in a minimal way, change the prediction to something else that I might be interested in. Okay. And so because everything is implicit, so we know the values of the features, because we start from some instance, we just usually use the numbers of the features. So in this case, we will use 1 to 3, 1 to 4, or just 4. Okay. So let's define objective and contrastive explanations. So before we define objective and contrastive, we define the weak version. So a weak objective explanation is also an answer to our question, is defined as a predicate, so a set of features such that for any point in feature space, if for the features in this set, the values are what we start from, then we guarantee that the prediction is what we are interested in. In contrast, a weak contrastive explanation is the answer to a why not question. And so if we are given a set of features, we are interested in finding some point in feature space such that if we fix the features not in Y, we are able to change the prediction. So essentially, we're saying if I can change the features in Y, I'm able to change the prediction. So for those of you familiar with the topic, this is very similar to adversarial examples in machine learning. So observe that, let me go back. So here I'm using a universal quantifier. It's easy to negate twice, of course, and we can see that the two formulations are very similar. And I'm going to talk a little bit about this shortly. So of course, we are not interested in just weak objective and weak contrastive. We are interested in subset minimal sets. And these are the contrastive and the objective explanation. So an objective explanation is a weak explanation such that any proper subset is not a weak explanation. And the contrastive explanation is a weak contrastive explanation such that any proper subset is not a contrastive explanation. So essentially, we are asking for subset minimality. So given these two definitions, we proved a few years ago that each objective explanation is a minimal eating set of all the set of the contrastive explanations and vice versa. And this I'm going to show you later in the talk. This is very important. And this goes back to the work of Reiter in model-based diagnosis from the 80s. So you could ask, okay, so where is logic besides the formulation? Well, we need to be able to encode how the model, the machine learning model, computes the output given some input. So this kappa of X here, we need to be able to encode it depending if we have a neural network, a random forest, a boosted tree, and so on. Okay, and so then we notice that this is just a consistency check or a satisfiability check, and this we can decide with some automated reasoning, SAT solvers, SMT solver, and so on. And so this is where SAT solvers come along. Okay. So before I show you a little bit more detail, let me give you an example, which I showed you before. So we have a decision tree, and we are trying to explain this concrete instance, 0, 0, and then 1, 1, and the prediction is 1. So we are here in the decision tree. So we can say that 1, 2, 4, 1, 2, 4 is a weak objective explanation because for any point in feature space, as long as x1 is 0, x2 is 0, and x4 is 1, we guarantee that the prediction is 1. So we say it's a weak XP, and we can prove that it's not subset minimal. So this is not just an objective explanation, it's a weak objective explanation. We can easily see that if we change the value of x2, the prediction will not change. So we can say that 1, 4 is also a weak objective explanation because for any point in feature space, as long as x1 is 0 and x4 is 1, we guarantee that the prediction is 1. Okay? And so in this case, we can prove it's subset minimum. So we can claim that 1, 4 is an objective explanation. So these are the type of explanations we are interested in. Similarly, a 4 is a weak contrastive explanation because we can find a point in feature space such that we fix x1 to 0, x2 to 0, X3 we don't change, is still 1, as we show here. And still we change the prediction because we change the value of feature 4. Okay? And of course, because we cannot make it simpler, it's subset minimal. So this is really a contrastive explanation. Okay? Notice that we can analyze in more detail the model, and we can list all the AXPs, in this case are these two sets, and the CXPs. And this we can essentially show by example that we have a minimal eating set duality. So 4 is a minimal eating set of the AXPs, and 1, 3 is a minimal eating set of the AXPs as well, and vice versa. Now, this is very important for computing them, and I will mention this later. So a different example with one more feature, again, a decision tree. So now the instance is 00111, so 00111. And we can say that 1, 2, 4, 5 is a weak XP. It's not subset minimal. And 1, 4, so it's enough to fix 1 and 4, and we guarantee that the prediction is still 1. So meaning I don't care about the value of X2 and X5, it's not going to change the prediction. And again, if I just change 4, I change the prediction, so it's a contrastive explanation. Okay, so again, we can see that we have minimal eating set duality. And this also shows that in decision trees, paths can be arbitrarily redundant. And this is an important result showing that we need, even if we have interpretability, we need to be able to explain the machine learning model. So so sometimes students ask, yeah, but decision trees are so easy. We are interested in very complex machine learning models, and this is really not it's not a conceptual challenge because we can encode in logic a neural network, and let me explain how this is done. So this is a very simplistic model of a neural network, but it's still a neural network, and with the exception of the first layer, each layer we view it as a block, where we compute an intermediate value x prime, given the input x. So this is x, and I'm going to compute here an intermediate value where I have the weights matrix and some bias vector, b. And then I'm going to compute the output given this intermediate value and some activation function. So this each of these nodes has an activation function. And for simplicity, I'm going to assume it's a ReLU activation function, which has this behavior. So if the input is negative, we just output 0. If it's positive, we just output the input. Again, this is quite standard. So we can, what I just showed in the previous slide can be represented as follows. X prime is the dot product of the weight matrix with X. Then I add the bias vector, and then a ReLU can be represented by a max operation. Okay. So how do we encode this in SMT or mixed integer linear programming? So this is a standard trick, and it has been around for 8 years now. So the dot matrix is a bunch of summations. So each summation is going to be shown like this. So I'm going to multiply a bunch of values by each feature and then add some bias. And I'm going to represent this summation by a difference of two non-negative variables, yi and si. And I'm going to assure that only one of them is non-zero. So I'm going to use a Boolean variable such that if it's 1, then yi is 0. And if it's 0, then si is 0. Notice that I'm asking both of them to be greater than or equal to 0. Since I'm forcing them to be less than or equal to 0, effectively, I'm forcing them to be 0. When zi is 1, yi is 0. When zi is 0, si is 1. So essentially, what I'm saying is that only one of them is non-zero. Okay? And as I said, zi is Boolean. So essentially, the idea is as follows. If this summation is positive, I'm going to assign it to the output. If it's negative, it's going to some select variable and disappear. That's the trick. So it's important to note that this, what I just summarized, encodes the computation of the output value of the model, given some input value. Of course, what we are interested in when we for computing abductive or contrastive explanation is to be able to decide whether or not we have the same class. So this also requires some encoding. Again, not very difficult to do. And so the bottom line is that logic-based encodings are not a conceptual limitation for XAI. So of course we have the complexity of reasoning, but that's it. Okay. So let me show you what has happened over the last few years. So from 2019 until 2022. So most of the results are from me and my collaborators. So first we show that several families of classifiers could be explained in polynomial time. So this is the case with decision trees, monotonic classifiers, naive Bayes, and so on. Okay, so essentially here we not only we are in polynomial time, but we have very efficient algorithms for computing explanations. For some other families of machine learning models, random forests, twisted trees, and decision lists, we prove that they are computationally hard to compute one explanation. But we show that in practice there are very efficient algorithms using, again, SMT or SAT solvers. And finally, until 2022, for some families of classifiers, including neural networks, we could really not explain very complex models. So we could explain neural networks with a few tens of neurons. Now, this changed somewhat in 2024. Several teams, ours included, show that for neural networks, using some a minor change of definition, we can scale to around 100,000 neurons, which is much more interesting than before. So essentially, there is progress still in the area. But of course, it's not just computing explanations. What happened is that essentially there is a field of symbolic XAI where over the years the topics have changed. So we started by analyzing what was the definition of explanation, objective or contrastive. Then we focused on neural networks, other types of models, random forest, and so on. And more recently, we have been looking at the feature attribution also with logic-based methods. Again, I'm not going to talk about this part, just to say that the field is very, very active in terms of research. Okay, so let me now talk about, again, I'm going to use decision trees because they are very simple. So and you saw this in some of the previous talks. But I'm going to start with tractability results, so nothing to do with SAT solvers. And then I'm going to show you two examples of using SAT solvers. Okay, so let's start with tractability. And let me give you an example. Again, this is important because logic explanations can be quite subtle. So this is an optimal decision tree, which was studied in a paper from 2019, NeoRIPS 2019. So this is an optimal decision tree. You cannot get a better decision tree than this one. And the question we asked is, if we have the instance 00101, so 00101, so we are here, what is the explanation in this case? So clearly we could say, well, if x1 is 0, x2 is 0, x3 is 1, x4 is 0, and x5 is 1, guaranteedly we are going to predict 1. The question is, can you do better than this? And we were puzzled to observe that, yes, we can do much better than this. So essentially, we can prove that features 1, which is trivial to see if we change x1, it doesn't change the prediction, but also x2 and x4 are irrelevant. And we can construct a truth table where we fix 3 and 5 and then change all assign all the possible values to 1, 2, and 4. And we can see that the prediction never changes. Okay. And so essentially what we are saying is that 3 and 5 suffices. So the rule, we can use the first rule, but for a human, it's very hard to understand. Or you can use this rule. So if x3 and x5 are 1, then the prediction is 1. And this is guaranteed. Okay. So for a human, it's much more intuitive to look at this explanation than the previous explanation. So this is the type of explanations we are looking for when we are computing objective or contrastive explanations. Okay, so how can we compute explanations in the case of decision trees? So we could use the definition that I showed you before, and we could use a SAT oracle. We have one of our papers talks about this, but of course it's worst case exponential time. It works well in practice, but it's still worst case exponential. But in this case, actually, we can do much better than that. So suppose we are here. So recall we are here, the prediction is 1. So if I want to guarantee that the prediction is 1, what I need to do is ensure that all the paths that go to prediction 0, so this path, and this path, will not be consistent. Okay? And so what I need to find is a subset minimal fitting set of this 3 paths, such that if I fix those features, the prediction will not be able to change. And finding this minimal leading set can be done in polynomial time. Okay, it's very easy to do. So let me now, again, I hope you can see this. If not, I have 3 demos. If this doesn't work, I will not do it. Let me share again. I hope you can see this now.
Yes, we can.
Yes, okay, thank you. So this is, again, I'm not, just a simple implementation of the algorithm I just described. So we start, the input is the list of CXPs, all possible CXPs, and I'm going to talk about this shortly. So in this case, again, for those of you of very good memory, these are the ways I have to change the prediction. And so if I come here, what I have to do is I start with the empty set, and then I go through the list of CXPs, and then what I'm going to do is I'm going to hit them with the features that I'm going to find in each CXP, such that I don't want to repeat things, and such that I cover all of them. So in this case, for example, it's again this one, as you can see. So I have 3 here, just 3, 5, and 2, 5. So you can see that I can hit the 3 with 3 and 5. So if I run. So if I come here and if I run it, it tells me that the XP is 3 and 5. Okay, so and of course it's all of this is polynomial time. Now, so what I'm saying is that if I fix 3 and 5, I guaranteedly will not be able to change the prediction. So the prediction is what I started from. So I have an AXP. Okay, so let me now. How do I stop the share? Give me a second. Not this one. Okay. Okay, stop the share. Let me go now to here and share again. And now share again. And here we go. So you can see now. So this is okay, very good. So now what I did is I just hinted you. The point was it's a very simple algorithm, so it's trivial to implement. Again, it's a few lines of Python code, not a problem. But there is a hidden information that I'm going to highlight now. So the idea is that if you have a decision tree, all the CXPs can be computed in polynomial time. Again, this is also a result we proved some years ago. So how do we compute? So I'm going to give you a different, I'm going to look at a different decision tree because it looks much more complex, but the idea is the same. So here, so if I suppose I'm here, so everything is 1. So I'm going to be here, okay? And I want, so I'm interested in the CXPs in this case. So notice that I could come here or here or here or here or here. So the algorithm starts with a list of CXPs, which is the empty set. And then for each leaf node that does not predict 1, so this, and this, what I'm going to do is as follows. I'm going to look at the features with literals that are inconsistent with my starting point. Okay, so for example, here, these 2 literals are inconsistent with my starting point and so on. Okay, so I'm going to add this set of literals to L. I'm going to remove from L the non-minimal sets, and that's it. So I have all this CXPs of the decision tree. So let's see an example because it's usually much easier to understand. So again, as I said, the instance is all 1s. So we are going to we are here and we predict 1, and so we are going to add 1, 2. Why? Because both features 1 and 2 have here will require different values from 1, 1. Okay. Then we add 1, 3. So we add 1, 3 because x2 keeps the value. So we don't need x2. Then 1, 4. 1, 4. Why 1, 4? Because here we keep x2 and x3. We need to change x1 and x4. So that's the only thing we need. And then 3. Why 3? Because to arrive here, we don't need to change the value of x1, but we need to change the value of x3. And finally 4, because we don't need to change the value of x1, x3, but we need to change the value of x4. Okay? And so now according to the algorithm, we need to remove the non-minimal set. So we need 3 and 4. This one goes away, this one goes away, and we need to keep that one. So essentially, we remove these ones, as I just said. And so these are the set of CXPs. Okay. Now, because of eating set duality, minimal eating set duality, which I mentioned several slides back, I can immediately say that the set of AXPs is, in this case, all the minimal eating set. I can construct 1, 3, 4, and 2, 3, 4. Okay. So again, this is looks a much more complex, complicated example than the previous one. So let's look at the previous example. And again, this is the algorithm. The instance is the one I analyzed before, 0, 0, 1, 0, 1. So we are here, okay? And so we have to add 3 because these two don't change, this one changes. And then 5, why 5? Because these two don't change, this does not change, this does not change, but this one changes. And then 2, 5, because we are here. So this does not change, this changes, does not, and this one changes, okay? And so again, I presume that it's easy to see that we don't need 2, 5, so we just need this one is dropped, so we have 3, 5, and now the XP 3, 5, and this is what I showed you before. Okay, so I computed it in polynomial time, but I could compute it also this way. Okay, so until now we have not seen SAT at all. So let's use SAT. Let's ask a different question. So let's ask the question: can I find the smallest AXP for a decision tree? So finding the smallest AXP is NP hard. This is a result proved 4 years ago. And so the idea, the way we tackle the problem is as follows. I need to make sure that each CXP cannot be made consistent. So I need to make sure that I cannot get to these nodes in the decision tree. Okay? So what I need to do is associate a Boolean variable si, which as a mnemonic is I set I, so I'm fixing I, so I'm not going to allow I to change. And I want so I have to eat each CXP, and I want it to be minimum size. So my preference is I would rather not fix any of the features. So this is very easy to encode as maxsat, and it's even simpler to implement in PySat. Okay, so what I'm going to do next, I hope, so let's first see the example, and then I'm going to show you the demo. So again, we have the same instance, and so let's see the maxsat encoding. So the CXPs are, as I said before, 3, 5, and 2, 5. This one, as I explained, we are going to drop it. It's not a CXP, it's a weak CXP. And then, so the hard clauses are 3 and 5. So I have to hit this guy and this guy. And the soft clauses are, I don't want to I don't want to S1 or S2 or S3, S4, and S5. So I would like them preferably not to be fixed, essentially. And so I can find a solution where I don't fix S1, S2, and S4, and I fix S3 and S5. So essentially, if I fix features 3 and 5, it's enough for the prediction, which we saw already before. Okay. Now, so let me go back. So this is, observe that this is only true for this concrete instance. If I change the instance, everything changes. So let's see what happens if I'm going to do 1, 1, 1, 1. So predicting 1. So essentially for this decision tree, I'm now in this node. Okay. So my question is, what will now be a smallest size XP? I think for some it might be intuitive. Let's see what happens. So first, the CXPs. So notice that now I have 1, 1, 1. So to come here, I need to change X1, X2, and X3. So I have 1, 2, 3. To come here, I need to change 1, 2, 4, and 5, which is this one. And to come here, I need to change 1, 4, and 5. So it's this one here. Of course, I put the last one, the one I'm going to drop, because again, it's not success minimal compared to this one. Okay. So essentially, the hard clauses are I need to fix 1, 2, 3, or 3. I need to fix 1, 4, or 5. And then my soft clauses are I would rather not fix any of them. Okay. And then I call the maxsat solver, which says, well, you can do this if you fix it S1, so if it fix feature 1, and then free all the other features. So essentially, which is intuitive. If I look at the decision tree, it says, well, as long as I fix feature 1, I'm done. If I fix feature 1 to value 1, I know the prediction is going to be 1. So this was rather intuitive. Okay. So again, this is a translation of the solution, the MaxAt solution, to what it means in terms of explainability. Okay. So let me do again the same thing I did before. So I'm going to jump here, and I'm going to come here and share again. And hopefully you can see again the code. Yes?
Yes. Good.
Okay, so again, this one was the 1xp, so this was a 10-liner, so it's very easy. So how can we do now finding the smallest with MaxSat using PySat, which I hope you have heard about. Again, it's just a wrapper around SAT solver such that it simplifies a lot the development. So essentially, the interface is the same. It's very simplistic. Again, I'm not even going to talk about it. I need to be able to read the CXP. So in this case, I'm going to read this 1, 1, 2, 3, 1, 4, 5. Okay, and essentially what I'm going to do is the computation is here. So the first thing I read the CXPs. Then I do a MaxSat encoding, which is done here. So I need to do the hard clauses. Okay, for each CXP, I'm going to say I need to hit one of the literals, and then the soft clauses are units that I have weight 1. So again, they are soft clauses. And then the model is just compute solve MaxSat. And then I need to be able to extract the XP from the solution. So essentially are the literals which have value 1. That's it. So let's see if we look at this example. So it should be clear that if I pick 1, I'm done. So I will hit both of the 2 CXPs. So if I run this, well, yeah, it works. So again, the point here is threefold. So first, if you have a decision tree, finding the smallest AXP is very simple again, it's NP hard, but it's very simple to model and very simple to solve using MaxSat and PySat. And that's it. So again, it's 20 lines of code or even less. Okay. So let me stop the share again. And share again. Let me go to this one. And share again the slides, which you should now be seeing. Yes?
Yes.
Okay, very good. So now what is ironic is that, so here I said we have decision trees, and we are going to compute the smallest XP for a decision tree. And again, it's NP hard, and we showed how we can do it with MaxSat. Ironically, in recent years, I've been studying sample-based AXP. So again, suppose you have a highly complex neural network. One way to explain is if you trust the sample, for example, if you trust training data, you can explain the prediction given the training data that you have. Okay, this is a fairly hot topic. And what is ironic is that the set of CXPs is again linear on the size of the sample. So this is very similar to what we have for decision trees. The set of CXPs can be computed in polynomial time, again, very similar to what we did for decision trees. And one XP can be computed in polynomial time, again, very similar to what we did for decision trees. More interestingly, computing one smallest XPs are NP hard, again, what we saw for decision trees. But what is ironic is that the MaxSat encoding that we have for decision trees can be used verbatim for the computing smallest sample-based explanation. So it's exactly the same approach. Okay, and so we have done that, and this was a paper last year at UQAM. Okay, continuing. So, how do we enumerate AXPs with SAT? So a few comments. First, so the enumeration of minimal eating sets can be attained in quasi-polynomial time delay. But to the best of our knowledge, practical evidence does not show advantage compared to a pure SAT-based approach. So what I'm going to explain is the pure SAT-based approach, or MaxSat-based approach in this case. So what we can do to enumerate the AXPs is we iteratively enumerate the smallest AXPs by non-increasing size. Sorry, my apologies, it's non-decreasing size. But I will fix this for the final version of the slides. So essentially, we can just use all the work we did before for smallest XP and then iteratively find the next max-out solution. And that's it. And we can enumerate all the XPs of a decision tree. Okay. Oh, observe, even though I have that in other talks, so the number of, whereas the number of CXPs is polynomial on the size of the decision tree, the number of XPs is worst case exponential. Okay. And so enumeration can take exponentially large time twice, right? So you are using max-out and then you are enumerating an exponentially large number of XPs. So I should have, again, I'm going to use the same trick again. So bear with me, please. So let me share the code again. So let's see how, again, I'm going to use the example. So this was the second decision tree, which was fairly complex. These are if you recall, the CXPs. And so how do we list them? So this looks a little bit more complicated, but it's not that much more complicated. So this is essentially what we did before. It's the same max-out code. That's it. And then what we need to do now is, instead of just finding one max-out solution, we need to be able to enumerate the max-out solutions. Again, something that many max-out solvers do anyway. Okay. And so essentially, I'm going to do this until I reach a target or until I'm done. Okay. And that's it. So let me, again, what I'm going to do is I'm going to run it on this example. So let me come here and I'm going to show you. So in this case, we knew already, because again, the number is very small, but we knew that if we start from, let me go back here. So if we have 1, 2, 3, 4, the minimal eating set should be 1, 3, 4, 2, 3, 4, which are shown here. Again, what the message is that all of this can be done with a few lines of Python code. Okay? And again, the same code can be reused for other domains, as I argued before. Okay, so let me stop the share. Let me share. No, I need to do something else here. Sorry. Yes, now it's working. I'm going to share now the presentation, which is this one. And now, yes, you can see this again. Yes.
Yes. So,
so this is just a very, very basic overview of the work with. Again, these are I covered some only decision trees. We have done neural networks. I showed you the encoding. We have done decision lists, boosted trees, random forests, monotonic classifiers, NBCs, and so on and so on. So again, this is just an appetizer for what can be done with SAT solvers in this space. And by the way, again, I tried to find examples suitable for summer school. In the case of random forests, and we have used, even though we can have very complex domains like real valued features, we have shown that we can use pure max-out based approaches for that. Okay. So again, but that would take much more time than what I was allowed to use. So again, our research is not just sometimes we prove results, of course, but we also have tools. And so this is a very small sample of the explainers that we've developed over the last few years. Some I did myself, some others former postdocs or former PhD students or former collaborators, still collaborators, okay? And again, all of them are publicly available. You can access them and play with them. So, in this talk, I started by giving you mentioning what was non-symbolic XAI. The point was just to say, you should not trust the results with non-symbolic XAI. And again, if you don't trust what I'm saying, you can read our papers and make sure that I'm not lying. Then I gave you a very, very high-level contact with logic-based XAI. So I introduced the concepts and I showed you what are the definitions, and then I highlighted with very simple examples how these things could be conceptually computed. And then I showed the connection between automated reasoners and explainability in the case of neural networks, the encoding, and in the case of decision trees, the two applications that I focused on later in the talk. So the concrete examples of applying SAT solvers that I covered are smallest XP, and I showed you how this can easily be done with existing SAT technology, and also enumeration of XPs again, and this can also be easily done with existing SAT technology. So if you ask, okay, so what are the research directions these days? Depends on the groups. So some groups and some former collaborators are still very interested in distance-restricted AXPs. So this is the change in definition that you need to consider to be able to scale for large-scale neural networks. So that's one research direction which is still active. A second research direction are sample-based explanations. There are a few groups that are doing this, and there are lots of challenges here. And then something that I've been focused on over the last year or so is explanations by feature attribution. So the idea is to use logic-based explanations to assign importance to features. Okay, and this concludes my talk. Thank you.
For the talk, do you have any question in the room? Yep, go ahead, please. What has been presented?
I cannot hear.
The mic is here. Oh.
Go there.
Yeah, I think you have to look at here or be close to the phone, or maybe it's not on. Or maybe wedge is not on there.
Yeah.
Can you hear me?
Yes.
Okay, so you have to show that the combination of neural networks with SAT and its usage for simple binary tree usage. What will like you to know, whatever you know is that, as for example, deep learning has been associated and has been developed for deep Q learning, H3C, and we have RBFs, we have Boltzmanns. Do you believe that could also be associated with those algorithms?
Yeah, you can. Of course. So as I said, let me. So give me a second. So what I did is I picked a simplistic model of a neural net, and I show you can encode it in logic. So if you have, again, there is no reason not to be able to encode it. You can encode it. So I see we have been criticized several tens of times by people in machine learning saying, well, you cannot use logic for machine learning. Well, that's not true. It's really not true. You can. So the challenge is not whether you can encode. The challenge is whether you can reason about it. Okay. So the difficulty is, well, to reason about these complex models is a challenge, but you can encode. So if you change, so suppose instead of ReLU, you use hyperbolic tangent, you can still do it. You can linearize it, and you can so you can piecewise linearize it, and then you can reason about it. It's not really a problem. Conceptually, it is a problem in terms of reasoning, the complexity of reasoning. So, but that's the simplistic version. Now, the fact that complexity of reasoning, of course, means, well, that it's not going to disappear. So as I said during the talk very quickly, we can now explain neural networks with, let's say, 100,000 neurons. These days, it's really small. For us, it's a huge achievement because we started from 20 neurons, now we can do 100,000 neurons. But for people doing machine learning, it's nothing. And that's why we have been changing our ways a little bit. And again, what I've said in the end, let me here. So what we have been focusing on is sample-based explanations. Now, this is exactly what people in machine learning did from the beginning. So for example, I mentioned the tool Anchors. Anchors is doing sample-based explanations. The problem is that Anchors is doing sample-based explanations without any rigor. And we can do rigor, okay? And so that's what we have been doing. So suppose you are going to train a very complex model with some training data. We can explain at least the behavior that you wanted with your training data. We can explain it in polynomial time, okay? And so that is something we have been doing. Of course, you could say that, well, yeah, but now I have the model. I want to explain the model. I don't want to explain the data. Well, Anchors, which people are using, is explaining the data. It's not explaining the model. So we are doing the same, and with rigor.
Another question? Online, you can watch. I have a question about the XAI for neural network. In case of neural network, the issue is reasoning about the huge neural network. Is it possible to do like not trying to find the best explanation, but to have like an epsilon approximation to be still able to have some kind of guarantee?
Yes, yes, that's a great question actually, because distance-restricted explanations are exactly that. Okay, so what people did is as follows. So first, we observed that explanations are tightly related with adversarial examples, and this has been a hot topic in machine learning for more than the last decade, since 2013. And since these contrastive explanations are tightly related with adversarial examples, if there are fantastic tools to find adversarial examples, then we should be able to compute objective explanations using that information. And so this is the insight that a group in Stanford and ourselves at the time in Toulouse had. So essentially what we did is we are going to use very effective tools for finding adversarial examples, and from those adversarial examples, we are going to compute objective explanations. The trade-off is that we have to be within some epsilon of the point we are trying to explain, as you just said. But that allows us to scale remarkably, so we can do very large neural net, explain very large neural networks these days. So that is the insight.
Thank you.
We now have a question online. I will read it for the people in the back. Is there a concept in XAI that matches this? Fundamentally, as long as you can explain LLM output as the replication of pattern observed during training, you can't tell whether the LLM is pattern matching or incorporating any of the knowledge that we use language to encode. Since those often coincide, example, nouns follow verbs is a viable pattern, and we use that pattern to encode world knowledge. Benchmarking in natural language is very hard to interpret, and even in my honest opinion, I think kind of useless sometimes. I feel like I make this argument over and over again. So if there is a quick term that would be so useful. So this is from
again, this is this is someone that has thought about these topics a lot. Thank you for the question. So I prefer to flip the nail. Okay, so so essentially what we have been doing is bring rigor to an area that has no rigor. Okay, so we cannot answer all the questions, and this one I cannot answer. But if people are so what is true is that people are using non-symbolic tools like SHAP or LINE or anchors, and now we can offer the same degree of scalability with rigor, which did not exist before. So let me give you an example. So can I explain LLM? Well, if you are going to use a tool like SHAP to do that, then I can. Should we use that? No, I don't think we should. Do I have a good answer? Well, I have some ideas, but no funding to work on them. So that's it. I cannot answer more. But so I don't think explaining LLM should follow the same path. It's much more complex, and so you need much more. So you need to change the paradigm a little bit. Again, as I said, we are waiting for funding for that. Thank you for the question.
Thank you. She says thank you too in the chat.
Question.
Tu peux aller en dessous du micro. Ben, le micro, il est là, tu peux aller en dessous du micro. Ouais. Il n'y a pas de caméra sur toi.
So I would like to bound back on what you said about what is the difference in symbolic versus non-symbolic, is especially the concept of rigor. So trying to bring rigor into a model. And more specifically, I would like to hear you talk about what is the very the complexity of rigor itself? Is it the constraints that are hard to implement themselves? Is it the probabilistic availability of those constraints? Is this more the generation, like you put it, minimal? You have some minimal challenge or to put. Is it this rigor that is difficult? What is the complexity of rigor?
Very good, very good. So let me try to jump around a little bit to try to answer the question. So this is what anchors computes. And again, we have found lots of examples where the rule that anchors computes is incorrect. Okay, it will fail. So it will mislead you with information. So it will, for example, it might. So you might not. Let me give you an example. Occupation should be white collar, for example. Okay, we have seen examples, not this one, but similar examples. So when I say rigor, is that you can have rules that are not really logic rules. So anchor finds rules that are not logic rules, given that we proved this in 2019, given the model. We were criticized because we were looking at the model and anchors does not look at the model. More recently, we proved that even if we just look at the data, anchor still gives you incorrect rules. So what should be the rule? That's when rigor comes along. So we have a mathematical definition of what a rule should be, which is this one here. Okay, so this is, we are looking at all feature space, and if we fix the guys that we are picking, then we guarantee that the prediction is this one. This is the logic definition of what a rule is, and this is what we say. This is rigorous. You cannot be more rigorous than this. Okay, so we start from a very solid foundation of what a rule should be, and then we also introduce ways to change the prediction in a very rigorous way. Again, logic-based definition. And then we started from here, and then we started computing explanations. I hope this answers your question.
I will have a question. So you show on the talk that for decision tree is not as simple as explainable as generally we think is are. So generally we say if you have a decision tree, is obvious that is explainable, and so you see that if you want to find the abductive explanation, is not as easy as we think. So do you think that we can have a model that is even simpler than decision tree that give us directly this abduction explanation natively without doing work?
That's very good. Actually, I have a visitor, and there are so if you have a linear model, then you cannot do better. So essentially, if I recall correctly, this was, and again, I have to give him credit. He was the guy that pointed this to me. Then AXPs will bring you no added value. So the model itself is the explanation. So there is one case, but it's a very simplistic machine learning model. So as soon as you jump to decision trees, decision lists, and so on, again, you need explanation. Again, I'm not saying. So I think the question is, so this is not to be viewed as a criticism. Again, I think I have papers on also finding smallest decision trees. So it's an important research topic. So the point is that even if you have a smallest decision tree, you need to explain anyway. So you cannot avoid that. The question that has not been answered, and I've been waiting for someone to answer it, is if we have smallest decision tree and we don't have a smallest decision tree, what is the comparison in explanation size? Okay, so the point I'm making is maybe, and again, I don't know, if we have an optimal decision tree and then we find explanations, we will be happier. So we have more succinct explanations than if we have a huge decision tree and then find explanations. But again, nobody has answered this question. I think that's a very important question to answer, to be very honest.
Okay. And in case of BDD, is it easier to find this?
So we prove that you can also find in polynomial time. So it's let me go back. Sorry, yes. So the XPGs are exponential graphs, and the BDDs fall into this category. So we prove we can find one in polynomial time. More than that, no. So for example, this very nice observation that the number of CXPs is polynomial. In the case of BDDs, it's not the case anymore. At least as far as I know. So that means immediately you are in trouble when it comes to finding AXPs and enumerating AXPs.
Okay, thank you.